So our next presenter is Professor Olivier Pfister from physics. And his general research is in atomic, molecular, and optical physics, with past interest in quantum measurements at the ultimate precision and various other parts that I'm not going to go through. I will note that he is a co-founder and CTO of the quantum computing startup QC82, and he is going to talk about measurement-based quantum computing leveraging quantum optics.
Thank you so much, Fred. Thank you for organizing this. It's really a thrill to be here, and it's fantastic to be walking in Stéphane's footsteps, because thank you, Stéphane, for this awesome introduction. This is going to be two things. It's going to be measurement-based quantum computing instead of circuit-based. So everything that Stéphane told you about circuits, quantum circuits, there's another way of making quantum circuits using measurements only, and I'll explain that, because that's based on what and then the second part of what I'll talk about is the hardware that we do at UVA. The UVA quantum computing hardware is specialized using light. We use optics, and there's a lot of us in the college and in engineering school who are really serious, have been serious about this for a while. So, go. There we go. All right. So all these little pretty graphs I will explain. This is research, okay, that's been steadfastly funded by NSF, also by DARPA and Jefferson Lab. We've had a really good, even though I'm not a nuclear physicist, quantum computing can be useful to nuclear physics, can be useful to a lot of different physics, solving the Schrödinger equation, basically, and also applications beyond that, because if you have really complicated molecules, you don't use the Schrödinger equation anymore. It's called chemistry. Well, theoretical chemists still use the Schrödinger equation, right? But it's becoming harder and harder as a molecule, like DNA, right? It's like, okay, all right, chill, right? And then now it's biology, and then it's psychology. I mean, the systems become bigger and bigger and bigger. You can't really do an accurate microscopic description at the quantum level. But if you have a quantum computer, you can, because exponentially faster. Bring it on, right? So that's why we're doing this, right? That's why we're doing this. We want to get into the regime where the quantum computers are powerful enough that maybe they explain how DNA recombines inside, the nuclei of the cells, and who knows, drug discovery, things like that. We're a long way away from that, but progress has a way of being exponential also sometimes. So I'm going to talk to you about, okay, measurement-based quantum computing and quantum optics. And I always want to pay a tribute to a giant in the field, Jeff Kimball at Caltech, who passed away last year and has been an inspiration for me in my work, and has been a true pioneer of quantum optics. So this is a big loss to the field. So rest in peace, Jeff. So this is, these are the guys at UVA who are working together. So we have Joe Campbell, electrical engineering, Andreas Behling, and Xiu Yi, and myself, and our good friend Mario Dagenet at the University of Maryland. And basically, I work in quantum sources of light. So I do optics experiments on the table, right? And I do fancy schmancy light sources. And Xiu does the same thing, but on chip. You can see, it's kind of hard to see, but there's a penny here, and there's tiny little rings on that chip. It's a piece of silicon nitride, probably, and each of these little rings there is the same as my big experiment with mirrors there, and crystals and ovens and things. And on the other side, when you have a light, you want to detect it, and Joe Campbell is a world expert on photodiodes and 3.5 semiconductor photodiodes. And Andreas is very good at putting those on chips. So you have those little channels of light, which is tiny, like micrometer wide, right? Like optical fiber, except all on a chip. So instead of having a chip that's like, a CPU or a GPU, we have electrical currents and gates and CNOTs and things. You have all little channels of light in there, right? That's That's our goal. And so we have the sources, we have the detectors, and in the middle, Mario is very, very good at separating different colors of light to be processed differently. So I'm going to give you some examples. There's another collaboration that's a little bit wider. That was a few years ago, we had an LDRD grant from DOE centered at Jefferson Lab in Newport News, and Robert Edwards, who's here with us and is going to talk this afternoon, was the PI. And Robert is an expert in lattice gauge QCD. You know, he has this little computer cluster. We have the Summit one at Oak Ridge in the background. There's a smaller one at Jefferson Lab. So he does, you know, quantum field theory and quantum chromodynamics on the lattice. Xinfeng Gao, who's here in materials, aerospace engineering, sorry, does the same thing for completely crazy nonlinear differential equations that describe very turbulent fluids and, you know, hypersonic fluids and such things like that. I'm going to turn that guy off. And all these are necessitate exascale classical computing resources. And if we throw quantum computing at that, we might just be able to go much faster. But you need to have a real quantum computer. We need to have the hardware to work. So we did some work, both theoretical and experimental. That was really to try to see how we could implement that on quantum optical computer. And so, okay, so it's great because I can piggyback on everything. We didn't talk with Stefan in advance to prepare our things, but turns out that now you guys know exactly what this is, right? You have how many qubits? 3. 1, 2, 3. Right? It's a circuit. You got one that has some quantum information. What is quantum information? Well, they're the probability amplitude of these two things, you know, whose squared give you the probability of measuring 0 and 1, right? But we don't know what they are because it's information. If you know, it's not information, you already know. You're not learning anything, right? It's like if I open a newspaper back in the day, or, you know, if I look at something on my screen, I fully expect not to know yet what I'm going to read. Otherwise, and it's less and less true, right? Like now people fully expect that they know what they're going to read, and that's the problem. Okay, those two ones are in state 0. So they're, you know, resource qubits. They're just there to help. Okay, what do we do with this? Well, so this slide is called the qubit there and back again, because I was looking for a good joke. So I ran it by ChatGPT and said, yeah, that's a very well-known thing. He said, well, how is it a very well-known thing? I just invented it, bitch. Sorry, pardon my French. And he said, well, you know, blah, blah, blah. It refers to quantum teleportation. So that's what it's about, quantum teleportation. And it's like, okay, find me a reference. And there was lots of references on quantum teleportation and Tolkien, because the Hobbit there and back again, of course, but none on who invented that pun, right? So yeah, like we're living interesting times. What can I say? All right. So I don't even care, right? I make dad jokes. I tell my students, I'm a dad. I make jokes. These are dad jokes. Bear with me. This is not stopping. All right, quantum teleportation as a quantum circuit. So what does that mean? Well, we have those two. So that part here, you're already, you know, deeply familiar with. It's making a Bell state. This is, okay, 0, it goes there. Nothing happens to it until it hits that guy. Okay, but this guy goes through Hadamard, so it turns into 0 plus 1 over root 2. But okay, I don't do root 2s anymore, right? And you can, if the, it's easy to renormalize. But then the 0 there does nothing, but the 1 there will flip, right? So the 0 does nothing, there's a 0 there, 0, 0. Plus, because you can have those crazy superposition of states, what does that mean? And Stefan was wise, saying, I'm not going into what that means, how quantum mechanics is weird, but people like, it's called old age disease, retirement disease for physicists. Like, what does quantum mechanics mean, right? But when you're doing, before then, when you're doing career, you have to publish and shut up and calculate. You know, it's like, okay, this is the interpretation of quantum mechanics. Yeah, we know how to calculate this, it works, so let's not think about this too much. But the state is both in 0 plus both in 1. And what does that mean? Well, it means, as Stefan explained, and you guys did with him, if I measure 1, I completely random it's 0 or 1, right? Because I got both terms and they have equal amplitudes. But if I find 0, then automatically the other is 0. No ifs and buts, it's 0. 100% of the time. But if it's 1, then automatically the other one is 1. So there's perfect correlation and perfect randomness at the same time, which means if I send those 2 qubits from a satellite to 2 different places of Earth, and people measure, they have identical random chains of qubits that you can use for encryption. That's called quantum key distribution. And the Chinese have done that out of a satellite in 2016, which triggered another Sputnik moment, triggered a bipartisan funding for quantum information. Okay, so this state is just here between those 2 qubits, 0, 0 plus 1, 1. Okay, and now this guy comes in, and this is, you can see that's the opposite of this circuit, right? And so what it does, these are detectors that measure if it's 0 or 1, right? But because of all that thing here that makes a Bell state, basically what this does as a whole is telling you what Bell states you're in, because there's more than one. There's 0, 0 plus 1, 1. There's 0, 0 minus 1, 1. There's 0, 1 plus 1, 0. And there's 0, 1 minus 1, 0. There's 4 of them. Right? They're orthogonal, et cetera, et cetera. So that thing, without going into details, tells you which Bell state it is. And it's completely at random. But when you do that, you have 2 measurement results. And then the qubit here ends up in that state. So there is 2, OK, that's the state psi that was here. So that's what's really, really interesting. Because we knew nothing about this, and none of that business in the blue boxes has anything to do with psi 0 and psi 1. None. Nothing, right? It's completely agnostic of the input state. But the input state finds itself down there with 2 gates that are Pauli gates, X and Z. That's the bit flip gate, and that's the I change the sign of 1 gate. And these one, they're applied depending on what the measurement result is. M1 and M2 are 0 or 1. So if it's 0, there's nothing. They're not there. If it's 1, they're there. I can undo them here. Because if you do them twice, it's the same as undoing them. And then at the end of the day, when all is said and done, you have this, what we call feed forward, which you decide to apply the gates or not, depending on what the measurement results are. And then we get the state psi here. Okay, that's called quantum teleportation. It's fantastic. And to, again, echo what Stefan said, when people wrote that paper here in 1993, and Stefan was saying quantum mechanics is easy to understand, they wrote that calculation to get this takes you, if you know linear algebra and how quantum works, it takes you 5-10 minutes. It's elementary algebra. What does that mean in the lab? It took 5 years to people worldwide to figure out how to do that in the lab, right? And the first experiments were not that glorious. Now we know exactly how to do it in the lab very, very well. But at the time, you know, transferring the quantum math to the actual physical systems, and even better to the actual engineering devices, that's where the challenge is, right? And so I like to think of myself as a quantum engineer. I think it's very cool. The coolest job I can have. So you can decide to remove the Pauli gates or not. Then you have them for free, right? They're there. And you can actually do something if you change the measurement. So you add a transformation to all that stuff here, like a single qubit transformation on each of those. And that transformation will be applied to the teleported state. OK, so, and you get that U of psi. I'm not explaining any more about that, but just by changing the measurement, you get to apply a gate if you teleport. And that's the original idea behind measurement-based quantum computing. It's like, OK, So I'm going to build a teleportation network. What do you need to have a teleportation network? You need this here. You need the Bell state. So you need to entangle a bunch of qubits together, and then you're going to need to measure them, and then, do feed forward, but that's very well informed by measurement results. Everything is well determined. But then, as a result, if you engineer your measurements correctly in the lab, you get to start applying gates. And as Stefan said, and somebody asked, how many gates, how many qubit gates, any n qubit gate can be realized with no more than single qubit gates and one entangling 2 qubit gate, like this guy. Right? That's the universal gate set. So you don't need any more than that. And teleportation is actually a one-way. So there's a little paper there from 1999 demonstrating the viability of universal quantum computation using teleportation and single qubit operations. And then on that, there were 2 remarkable papers by Brigel and Rassendorf where they really put that general insight to concrete use by making those, okay, so, you take qubits, each node of that graph is a qubit, and this is an entangling gate. It's not a CX, it's not the C0 that we've used so far, it's a CZ, same difference. Let's not go there. Right? Trust me, it works out. The math is not that hard, but basically the math is here. If you put all the qubits in like a Hadamard gate after a 0, right? 0 plus 1, 0 plus 1, the root 2s are gone, but they're there, right? They're just not shown. Then if I have 2 qubits there and they're not connected in any way, okay, they're just 2 states that are factorized. And then I put a CZ gate between them, and they have to be both in plus, then the state is like that. So it's all 4 qubit state, but there's a minus here. And then if you try to refactorize it back, you can't get 2 independent. You have a Bell state. You have 1 qubit is in 0, the other one is 0 plus 1. That's what the plus means. If the other one is 1, then this is 0 minus 1, right? And those things are orthogonal. And so you have, again, those correlations. If I measure the first qubit, I get 0, the other one is in 0 plus 1. If I get 1, the other one is a 0 minus 1. And those 0 plus 1, 0 minus 1 are orthogonal. They have nothing to do with each other. They're completely distinguishable. They can't happen this one or the other. Okay, so this is fine. This just says I can entangle my 2 qubits with the CZ gates, and then I make a big network square grid lattice. And then the big result of this paper by Rassendorf and Brigel, which they called a one-way quantum computer, is that, well, if I measure all my qubits, once they're in that square grid lattice, if you can make that, then all you have to do to make any gate, you just have to measure each individual qubit, and the neighbors have to know about the measurement results. And using the feed-forward like we did in teleportation, you can implement any gate you want, including the whole universal gate set. So that's the whole thing. So when I learned about this, so 2001, right? I started here in 99. And I thought, gee, it would be cool to make cluster states, right? These things. And I think with light, I had to get tenure first. And then after I got tenure, doing just 2 qubit stuff, like let's not go crazy just now. So in 2003, it's like, okay, it looks like I'm going to get tenure. All right, so let's go crazy now. And so, yeah, you have to keep your priorities straight. But this is what's left. Okay, this is a picture from this, where you had an initial square grid lattice, and then you do measurements. So these are represented, the qubits, the 0 and 1 are like spins. And so the 0 and 1 in this picture are the spin point, an arrow pointing out of the screen or into the screen. This is just like little magnetic moment, magnet dipole moment directions for a qubit, like an electron or something that has 1/2 spin. But you can also measure the spin perpendicular to that direction, and even at some weird angle. And turns out that this is, once you make all the measurement, this is kind of the circuit that you're getting with an entangling gate here, an entangling gate there, some single qubit rotation gates there. And this is actually a circuit, but it's based on that little entangled state. Okay, so you have measurement, which is random, but you have feed-forward, which is deterministic. So it always works. Because people sometimes think, oh, measurement-based quantum computing, because when you do measurement in quantum mechanics, sometimes you get this, sometimes you get that, and it's random. So how is that ever going to work out? Well, because we have the feed-forward, we have the measurement results, they are random, but then we are changing the neighbors on the graph accordingly, depending on what we measured, what we got for the measurement results. So we always win. We always fall back. Like the cat, not Schrödinger's cat, the regular cat, always fall on their legs when they fall. Yes? Yes. Yes. So that's a great question. You cannot send a qubit. Well, you can send a qubit if you put like your quantum particle in a bottle and you take the bottle with you. And there, okay, that's fine, it works. But here you have two qubits, and one is in, and there's a third one. It's in a given state, and you entangle those two qubits, and let's say these are the same location. And then when you're done, the measurements are at this location, and then the remote location is that guy, gets the classical information only. That qubit is absolutely nothing to do with the quantum information, and boom, right? And the measurement results are 0 or 1. They have nothing to do with psi naught and psi 1, right? So there's absolutely nothing about the quantum state of a qubit, but the quantum state itself is magically, it's really teleportation, like, So if you imagine that my body is in a quantum state, in a pure quantum state, I would have to have a blob of organic matter in an undescript state over there. And then, I do, you entangle me with another blob, which was preliminary entangled with the other blob. And then I disappear here, but I will reappear in a, by virtue of if we're good enough at processing quantum information for the whole human, which I think is, okay, not gonna, but it's good sci-fi material. It works. Ask Michael Crichton, and he's written a book about that. Does that? Yeah, digression. Okay, so I'm gonna tell you how we made cluster states, right? So with it, like after I got tenure, I decided to make cluster states, and well, I did. So then, and now she is making them on chips, and we're moving on. So I'm gonna go a little bit faster because I don't have all afternoon. Otherwise, I would take all afternoon, but. So yeah, you can do teleportation different ways, you do things like that. Cluster states are funny because if you measure in the middle, then you can cut them. If you measure something else in the middle, then you can bridge them. And you have a complicated guy like that, you measure the qubit in the middle there, and boom, you get, So you can shape the cluster states by measurements. Not only can you implement gates, you can actually cut and bridge them the way you want. So you can cut channels, you can bridge things, you can reconfigure just using single qubit measurements. And really, physicists, if you ask a physicist to, oh, make me quantum gates in the lab, said, okay, all right, entangling. But if you ask a physicist to measure stuff, say, oh yeah, oh sure. What do you want to measure? What's the error bar that you need? Oh, that error bar. Ooh, that's barely an error bar now, is it? Okay, that's quantum error correction. Okay, so we're doing this, instead of qubits, we're going to use Q modes, which are electromagnetic field. Think of light at a given color. Right? It's an electromagnetic wave, it's an electric field and a magnetic field. We're going to measure the electric field. That's our qubit. Instead of measuring 0 and 1 or spins and things, we're going to measure the electric field. We do that by doing interference in optics. We can also measure the photon number, and that's actually what you need to do if you want to correct errors. So we want a ton of qubits. These are the two big challenges of quantum computing. You need a ton of qubits, like Stefan showed you how it scales when you increase the number of qubits. And people are going, people who are serious about doing quantum algorithms are going to change the world. you need 1 million qubits, physical, right? So you can't, 150, that's cute. That's not anything. It's just cute, right? If you want kick-ass, it's 1 million, right? So that's the thing. What's the path to scalability? Then you can evaluate the different platforms, trapped ions, superconducting qubits, trapped atoms, photonics, to see how much it will scale. And well, photonics has the best scalability potential. But you also need to correct errors. And for error correction, there's been demonstrations in trapped ions that are the cleanest qubits around by far. You know, superconducting qubits and atoms are close behind. Photonics is getting there, but started 10 years later, so it needs to play catch up on that. However, for the scalability, we're looking really good. So, okay, so we have this wave-like thing, which is we work with fields, and this particle-like things, which is we work with quantum fields of light, and therefore we have to deal with the photons, right? The grains of light, if you look at how much energy there is in an electromagnetic wave, in a beam of light, well, it's the number of photons. Okay, so I'm told that my time is up, so I'm gonna flash a few things really quickly so that you see that at UVA. So we're like, this is math, okay. This is how we do this. Why do we do this? Because it scales. There were jokes in there. There were jokes, I promise. We make sources of light that emit photon pairs. So you have 0 photon in one beam and 0 photon in the other beam, or 1 and 1, or 2 and 2. You see those amplitude there, they actually decrease exponentially, or 3 and 3 and 4 and 4. So you never know how many photons you're going to get if you measure one beam, but the other one, if you measure 1 and you find 3, how many photons does the other one have? I have 3 here. I have 3 there, right? And so it's entanglement. It's the same thing. So we make those sources, they're entangled, and we can build quantum graphs. Okay, math. So this is a laser, emits photon by photon. That's the spectrum, the different colors of a laser. This is our particular source of light, and Shuyi does the same thing on chip, photon pairs by photon pairs. And so now we have quantum correlations inside the spectrum, the emission spectrum, and it's freaking awesome. And then, oh, can we make entangled states? And so we started like, this is the first post-tenure paper. And so, yeah, we met like really clever young theorists who helped me figure it out. Yeah, we can make, these are cluster states. This is a real cluster state. It's a theoretical paper, right? And then we started making experimental things where we have pairs of pairs. So we have like signature of quantum noise reduction called squeezing that tells you, yeah, there's entanglement here, and there's entanglement there, and there's entanglement there. And that's the frequency spectrum of our quantum source, right? It's a laser beam that's coming out. It's an exotic laser. And there, between frequencies, you have photon pairs. You have entanglement teleportation channels, right? All over the spectrum. And as far as we could measure, which is 60 modes. And then we did, okay, Shu did that on chip. Ask Shu, next talk. We did more complicated, like instead of pairs, we need 4 entangled at a time. Complicated experiment. I will not lie. Ask me what we did. It works. And then, yep. And then we did that. That's 60 together. It's probably 10,000, but we could measure only 60. This is a cluster state. This is entangled, all of them together. And we measured, and again, signature of each edge of a graph, and okay, it works. All right, and we have some colleagues around the world, in Paris, in Brazil, in Japan, 1 million entangled qubits of light. Scalability, done. So now they did that in 2D also. We have papers in 2D, 3D. We haven't done that in the lab yet. We're working on this. The photons, you want to measure photons? We can measure photons. NIST has machines that call superconducting transition edge sensors. You can measure photon number. You have those different signals from 0 to 17 photons in a laser beam. We can measure photons. This is a huge deal because it's very, very difficult to make those machines. Joe Campbell and Andreas Billing are working on making those detectors. These are superconducting. They work at cryogenic temperatures. We want to make them at room temperature with semiconductors instead of superconductors. So that's work in progress. And then you can do quantum error correction. And, these specific quantum states have been done in trapped ions, superconducting qubits, 2025 Physics Nobel Prize, Michel Devoré here at Yale, and in optics also in two different, in my groups, where also use machine learning. I'm going to stop there because I've exceeded my time. Thank you very much.